Okay, this is going to be a video recording of the last information in Chapter 9. Alright, so we ended up talking about molarity, and the next part of molarity is to deal with a dilution. And a dilution is whenever you add water to the solution that you already have and make it more dilute. So in the picture that they have here, you can see that we've taken 1 can of the frozen orange juice concentrate. We're adding 3 cans of water in order to dilute it, and then we mix it up, and that makes a diluted solution. If we need to do any calculations, then the moles of the diluted should be equal to the moles of the concentrated, because in the example with the orange juice, we had 1 can of orange juice concentrated at the beginning. That's the same as the 1 can of concentrated orange juice at the end. We had just added more water. So we can use a relationship for molarity times the volume of the dilute would equal to the molarity times the volume of the concentrated. So next we'll do an example. So in this case it asks how many milliliters of a 12 molar solution is needed to make 250 milliliters of a 3.5 molar solution. We use M1V1 equals M2V2. Now this is my concentrated, and then this is my dilute, and it doesn't matter which side I put where. So I have 3.5 molar. I'm going to leave my volumes in milliliters. On the other side I have 12 molar, and I want to find the volume. So I'm going to take 3.5 times 250 and then divide by 12. Okay, and when I do that, I found that my volume is going to be 72.9167. I'm going to need 2 significant figures because that's the least number, which would be 73 milliliters. So it means I'm going to take 73 milliliters of my concentrated solution, then I'm going to add water to that until I have a total of 250 milliliters. Now, we're going to go on to chemical reactions, and we need to remember our stuff from Chapter 7. And we're going to be using those same 3-step problems that we were doing before. Now, the first thing you always need to make sure that your equation is balanced. After that, we always find moles of whatever substance we can. Then we're going to convert the moles of one substance to the moles of another one, and to do that we need to use a mole ratio. And then finally we're going to ask what we're ever asked to solve for, which could be grams, it could be liters, whatever it was in that problem. So here's one. It says how many liters of a 3 molar HCl, so this is 3 molar, and I have 4.85 grams of the calcium carbonate, and here I'm looking for liters. So the liters is what I'm going to be trying to find. Now, I can't find moles out of that because I don't have enough information, but I can find moles of that. So to do that, I'm first going to have to find the molar mass of calcium carbonate. So I'm going to add a calcium plus a carbon plus 3 oxygens, add all of those up to get my molar mass. So 4.85 grams. And that's CaCO3. My molar mass is 100.07 grams in 1 mole. So I'm going to take 4.85 and divide by that molar mass. Now, I'm asked to find something about HCl. So now my second step is to do a mole ratio between CaCO3 and HCl. So I have 0.04846, and this is moles of CaCO3. I want to find HCl. CaCO3 is a 1 in my balanced equation, and HCl is a 2. So I'm going to cross multiply and then divide. So that leaves me with 0.0969 moles of HCl. Now I need to find liters, and I have my molarity. And I know that molarity is moles over liters. So the molarity I have is 3. My moles is 0.0969, and I'm asked to find liters. So I want to cross multiply and then divide. And I get an answer of 0.0, and I'm going to need 3 liters. Okay, so my 3 steps: divide by the molar mass to get moles. Then I did a mole ratio, and that's stuff we knew how to do before. This was the only new piece, was I used my molarity equation that we learned before, and I plugged in the moles that I just found along with my molarity to find my volume. Okay, so here's going to be another example. My equation's already balanced. This time I have 22 milliliters and 0.10 molar. And then I have 15 milliliters of this, and they want me to find the molarity. Now this is not a dilution, so I cannot use MV equals MV, the one that we use for dilutions. I'm going to have to do my 3 steps. So my first step is to find moles. Well, since I have these 2 pieces of information, I should be able to find moles, because molarity is moles over liters. And I have the molarity, and I can find the milliliters. I have to move it over 3, so 0.022. So now if I multiply those, that's going to get me my moles. That's my first step. My second step would be a mole ratio. So I have 0.0022 of the MgCl2. I want to find AgNO3. In my equation, I have 1 MgCl2, and I have 2 AgNO3s. So I'm going to cross multiply and divide. Now I have moles of AgNO3, and they want me to find the molarity. So molarity is moles over liters. I don't know the molarity, but my moles I just found. My liters, have to move that over 3, so 0.015 liters. And I get 0. I'm going to get 2 significant figures, 2.9 molar. So once again, we had 3 steps. This time I did the molarity equation, then a mole ratio, and then the molarity equation. But the first step is to always find moles however you can. Next step is do a mole ratio, and then third step is find whatever is needed. Okay, we looked at solutions, and now we are also going to look at colloids and suspensions. So we know that in a solution we have a solute and a solvent, and that they're all mixed together, and I can't really tell one apart from the other one. Most of the time we can see through them, they're transparent, and the particles are so small that if you would go through a filter or through any kind of a semi-permeable membrane, they would go right through. In the case of a colloid, those particles are much larger. They still look all the same throughout, but they're not going to settle out. But the particles are just thicker. And these particles can go through a filter, but they are not allowed to go through a semi-permeable membrane. And colloids are things that are thick. These would be like fog or smog or smoke. Those would be colloids. And here you can see that they've given you several different kinds of colloids as far as what is dissolved in what. Now suspension, in this case I can tell the two things apart. These particles are so big that now I can see them. And they are often so large that they're going to settle out. So that means if you just let it sit, you're going to see these particles sit at the bottom, and you have to stir them up in order for it to stay suspended in there. These particles are large enough that we could filter them out, and they could also be, they can't go through a semi-permeable membrane. A lot of your children's medication like liquid Tylenol, milk of magnesia, liquid penicillin, all of those things are things that you have to shake well before using. Those are your suspensions. This table will be very helpful as you do your assignment because they have each one of the categories, the types of particles, whether or not they settle out, and how you can separate them. So you want to be able to refer back to that. Last thing, well, there's two things left. One is colligative properties. Colligative properties are things that change depending on how much you add, not necessarily what you add. And the two main ones are the freezing point and the boiling point that we're going to look at. So anytime that we add something to it, it's going to lower the freezing point, meaning it's not going to freeze at the same temperature. It has to get colder before it freezes. And it's also going to increase the boiling point, which means it won't boil at the same temperature. It's going to have to get hotter before it boils. Example, if we add salt to water, it's not going to boil or freeze at 0 and boil at 100 anymore. If we add salt to it, it's going to have to get colder before that will freeze, which is why we put it on icy roads. And if you add salt when you're cooking pasta, that means it's not going to boil at 100, it's going to be boiling at a higher temperature, and the advantage of that is that it's going to cook faster. Here they're showing you for pure water, the freezing point 0 to 100. If we add a non-electrolyte, it's going to change the boiling and freezing point. If you add an electrolyte, then I get, it depends on how many moles of solute particles I have. So here I have 1 Na and 1 Cl, so that's 2 moles. So I get almost twice the difference. And if I have one that has 3 particles, then I get an even larger difference. So if it's a non-electrolyte, I just get my regular difference. But then if I have something that's ionic, which is an electrolyte, I get an even greater difference. Next thing that we want to talk about with colligative properties is osmosis. And osmosis means that if we have a semi-permeable membrane, water is able to flow through that semi-permeable membrane from lower solute concentration to the higher solute concentration. And solute means the stuff like the salt or whatever it is I have. So the level of the solution with the higher solute will rise. The one with the concentration of the lower one will become smaller, and that's going to continue until the two solutions become equal as far as their rates and their concentrations. So here's a picture. I have a 7% starch, and over here, or this was a 4% to start with, and this was a 10%. So what's going to happen is the 4% that's over here, water is going to transfer over to the 10%. As it does that, the 10% is going to become diluted to 7%, and as water leaves, this one becomes more concentrated, and that eventually they're both going to become the same concentration, and in that case the amount that's going back and forth are the same. So water leaves this one, this level gets lower, water goes into this one gets higher. And osmotic pressure is the pressure that is going to stop the flow of osmosis. So if we go back to our old slide, the water was wanting to come over here. The osmotic pressure would be the amount of pressure that has to be applied on this side in order to stop the flow of water coming over. And that osmotic pressure gets larger if there is more particles in the solution. So if I have an even greater difference between these two solutions, like one was 4 and one was 10, if I make that even a bigger difference, then the osmotic pressure is going to increase. It's going to take more to stop it. Okay, so a semi-permeable membrane separates a 10% starch solution from a 5% starch solution. If starch is a colloid, fill in the blanks in the statements below. So I have to decide which solution has the greater osmotic pressure, and the one that has the greater osmotic pressure is the one that has the biggest concentration. So that's going to be solution A. Water is going to go from the one that has the lower solute concentration to the one with the higher solvent concentration. So that means it's going to go from B into A. So in that case, they want to know the level of solution and which one is going to be lower. So if water is going out of B, B is going to get lower. And you can see those are the answers that we got. When we look at blood, we have our red blood cells, and those have semi-permeable membranes. And they want to have an osmotic pressure that stays the same. If the osmotic pressure is changing, then that's going to cause damage to the cells. So we have to have an equal amount of flow of water into and out of the red blood cells. So if this is my red blood cell, I want to look at the surrounding solution, and I want the amount of water coming in and going out to be the same. If they're not, that's going to cause damage. If we have an isotonic solution, then that means the osmotic pressure in and outside the cell is the same. And in that case, we're going to have an equal flow of water in and out of my red blood cell. And for isotonic, that means it's going to be at 5% glucose or 0.9% salt. So 0.9 sodium chloride and 5% glucose. Those are both isotonic. A hypotonic solution has a lower osmotic pressure than the red blood cells. So that means water is going to flow into the red blood cell, more water coming in than going out. That means the cells may swell up and eventually burst, and that condition is called hemolysis. If we have a hypertonic solution, hyper is like kids are too hyper, too much energy. So hyper has a higher osmotic pressure than the red blood cells. That means water is going to flow out of the red blood cells, and this is going to cause the red blood cells to shrink in size, and that causes a condition called crenation. All right, so in this case, we can see these ones are isotonic. These are what my normal red blood cells look like. This is hemolysis, where these are swelling up, and you can see there's little dips in here. These dips are not as big because water has come in and it's caused these to swell up. This one, these are all shriveled up, and that's crenation. So shrinking in size, and then the other ones were expanding. All right, so we have to decide if the solution is isotonic, hypertonic, or hypotonic. So we need to go back and see what it meant to be isotonic. So 5% glucose or 0.9% sodium chloride. So 5% glucose or 0.9% sodium chloride. That's what it means to be isotonic. This is supposed to be a 5. All right, so I can tell right here, this one, 5% glucose, that's the same. So that's got to be isotonic. Okay, we'll just go backwards here. 0.5% sodium chloride, I'm supposed to be 0.9. So 0.5 is lower, so that means it's hypotonic. 1% glucose, 1 is less than 5, so again that's hypo. And then 2% sodium chloride, 2% is greater than that, so that means that one's going to be the hypertonic. So those are the answers that we found. All right, now I have to decide if the blood cell is going to be the same, meaning it's isotonic. If we're going to go homolysis, which means it's going to be hypo, or if it's going to undergo crenation, which is hyper. And this means it's isotonic. All right, and again, we're 5% glucose or 0.9% sodium chloride. So if we have 5% glucose, that means it's isotonic and nothing's going to change. Okay, if we have a 1% glucose, that's less than that. So that means it's going to be a hypotonic solution, so we're going to go homolysis. 0.5% is less than sodium chloride, so that's a hypo. And 2% is greater than this, so that means it's going to undergo crenation. And those were the same answers that we found.